All right. My name is Miryung Kim. I'm an associate professor in computer science department at UCLA. And today here, I'm with my PhD student, Muhmammad Ali Gulzar, who's been doing wonderful work on debugging of a big data analytic application written in Apache Spark. In the past 4 years, my research group has been working on software engineering tools for data science. In particular, we've been focusing on debugging and testing for big data analytics application written in Apache Spark. Today, we're going to demonstrate our capability of enabling automated debugging for Apache Spark application. As the big data is becoming more important, data scientists are increasingly using data-intensive, scalable computing platforms such as Google's MapReduce, Apache Hadoop, and Apache Spark to write big data analytics application. This is how development process goes. Developers write applications locally using only a small subset of data downloaded from terabyte-scale data warehouses. And once they are done with the local debugging and testing using this small subset of data, they submit the job to work on the cloud on the entire data set, like usually terabytes of data set. And then after application is run, they may get a job failure or crashes, or they may get error job result that may look suspicious. Then data scientists spend enormous amount of time going through this post-mortem log to find the root cause of errors, and they fix application or data hoping that something works, and then they repeat this process. Compared to traditional software development or engineering, really debugging big data analytics applications is in the dark age. To address this problem, for the past 4 years, my group has been doing some work on debugging for Apache Spark application. So today's talk is about automated debugging, but let me briefly describe our prior work on interactive debugging and data provenance, which are sort of building blocks for our automated debugging capability. This first piece of work on interactive debugging was presented at International Conference on Software Engineering, which is a top-tier conference in software engineering. We also demonstrated our BigDebug tool in Spark Summit last year. As an academic researcher, we're proud to say that our research on debugging has inspired a few tech companies to follow our line of work. For example, Pepper Data implemented a version of our idea on debugging in their Spark code analysis tool. So this shows sort of our group's research on industry impact. And let me go through some of the high-level details. So our interactive debugging provides this primitive to enable interactive debugging. You might be wondering why interactive debugging is hard in Apache Spark application, because we had tools like GDB in traditional software development for years. The reason why it's hard is because these big data analytics application, when it's running on the cloud, we cannot just pause the computation because it interferes with the performance and throughput of the entire cluster. And also, it's difficult to actually inspect the terabytes of data flowing through a particular watch point or a variable, because there is literally terabytes of data, and it doesn't make sense to ship those data to a local computer. So what we have done in this work is that we designed a simulated breakpoint, which emulates sort of a breakpoint and ability to incrementally regenerate the program state and program snapshot from the latest materialization point. We also designed on-demand guarded watch point, which enables the data scientists to ask a query about or fetch the data they need that matches the predicate. These predicates could be actually modified at runtime. What we internally do is that we recompile this predicate, dispatch it to the distributed node on the cloud so that we can fetch the data that matched and automatically streams this matched data to the user. Currently, when crash occurs, people get an error that this task node failed after this much time with this exception. but they cannot actually understand the root cause of an error or even remediate this failure at runtime. So what we have built is a crash culprit identification and remediation feature, which allows the user to see which data is failing, being able to query what is the source of input record that's leading to this crashed input, and being able to actually modify this record at runtime or apply code fixes at runtime. Again, we recompile and apply these patches on the distributed node at runtime. And we also allow backward and forward tracing feature, meaning if a user wants to know the origin of a data record that's producing a particular output or a crash culprit, we allow people to actually go and identify that subset of an input. And this is built on our capability, which is called the data provenance. So this work on data provenance is basically re-architecting Apache Spark runtime to provide this forward and backward tracing capability at a fine-grained record level. And this work we presented at VLDB, which is a top-tier conference in database systems in 2016. And this is a collaboration work with my colleague, Tyson Conde. So what is a data provenance? Data provenance is this a problem where given the output of a query, you may want to identify a subset of input that's leading to this data. So for example, if you have a relational query like this and the input table, you may get an output that may look suspicious. For example, average temperature looks very suspicious. You may want to go back to the origin of input that's leading to this output. You might be wondering why we don't have this data provenance feature for Apache Spark right now. Actually, there has been some effort to provide this lineage or data provenance support for data-intensive scalable computing, in particular Apache Hadoop. However, what people have done is that they were trying to store this input-output mapping in an external storage, often relational databases, and it required people to also write separate queries and run those queries on external databases to answer this data provenance query. So what we have done in our work is that we actually instrumented this Apache Spark runtime so that we can generate input-output mapping, and we efficiently store them as a part of an in-memory block manager, which is a sort of native support that Spark provides. So this tagging was done at the stage level. Then, when the user asks, what is the origin or subset of input leading to a particular output, we run recursive backward join queries to answer this question. So for example, given this output ID, we can go back and do backward recursive join to answer the questions about which particular input is leading to this output. I'm not going to go into detail of our work, but what we have implemented is actually distributed, optimized join that uses the partition ID information to significantly reduce the cost of a recursive join. These are building blocks, and now we're going to talk about our recent work on automated debugging of Apache Spark application. We presented this work at ACM Symposium on Cloud Computing last year, and today we're going to also do a live demo of this tool as well.
All right, so I'm going to start the rest of the talk with the help of a motivating example that will actually motivate the problem that we are trying to solve in this piece of work. So let's assume that Alice is a Spark user, and she have written a Spark program to identify for each state in the US the difference between the minimum and the maximum snowfall reading for each day of the year and for any particular year. And the data set that we're using here looks like this, where you have the zip code, the date of the measurement, and the actual measurement of that snowfall reading. So a normal Spark program. So now she runs this program on a large data set, and she have implemented this program using these usual data flow operators like flat map, group by key, map. And once the execution has been done on the cluster, she retrieves the output. And by inspecting the output, she sees that some of the outputs may look suspicious. I mean, in this case, you can see that the snowfall reading for Alaska looks like a 21,000 millimeter, which is even for Alaska standards, it's too much. So at this point, she must be wondering what are the input records that are actually responsible for generating this suspicious output. This task is non-trivial because the data has gone through these multiple transformations, and it's really hard for Alice to actually see how the output is connected to which inputs. And also, you have huge data sets, so obviously it's not feasible to just manually inspect these input records by hand. So at this point, the problem is, given the program has run and you have some test oracle, what are the minimum inputs that are actually responsible for generating a suspicious output? And we have two approaches that are pretty common in solving this kind of work. So let's say Alice decides to use data provenance that Miryung had just presented. So in data provenance, what we're doing is we have the output. Alice asks data provenance to do backward tracing of that output and to find input records that are responsible for generating that suspicious output. At the end of this process, she gets some subset of data, but that subset of data is usually an over-approximation of the actual input that should have been returned in the first place. And this is because data provenance works on key-value mapping, so all the input records that have the same key as the faulty output record, they all are marked as faulty records, while only one of the records might have been responsible for generating that faulty output. So the other approach that we can use is it's a really popular software engineering technique called delta debugging. So delta debugging works, it's a binary search-like strategy where a user can split the task, split the data in different portions, and try different subset of input data and test it to see which precise subset data actually produces a faulty output again. So what happens here is delta debugging takes in a test oracle function and then splits the data in half, try the first half of the data, that half fails, and then delta debugging knows that the problem is in that half of the data. Then it again splits the data in half, try the first half of the data, that passes the test. It tries the second half of the data, that also passes the test. Then it tries more finer-grained configurations of the input. So let's say start with by removing the last element, it tries to test the first two, and then it tries to test by removing the first two elements, tries to test the other one. And similarly, you just go on and keep on doing this repetitive procedure until you get the most precise input records that are responsible for generating test failure again. So as you can see, delta debugging takes many reruns of the same application to find that precise input records responsible for a test failure. So assuming that you have terabytes of data, it may run like 300 times to just figure out where what's the precise set of data is. So to overcome the limitations of both delta debugging and data provenance, we came up with this really innovative technique called BigSift, which actually combines data provenance with delta debugging, where data provenance removes the irrelevant input records that are not responsible for generating a test failure, and then it applies delta debugging to figure out what is the precise record responsible for a faulty output. But by just combining data provenance and delta debugging, we cannot perform feasible debugging. It still takes a really long time. So we have to go one step further to implement optimizations such as test predicate pushdown and several other optimizations that actually help us to achieve feasible automated debugging. So for the rest of my talk, I won't go into the details of how data provenance and delta debugging works, but I'm going to go into what these optimizations are. So by looking at the backward traces of different programs, we observe that sometimes when we do backward trace, only few partitions are actually responsible for producing a faulty output. And this gives us this idea that why not just test individual partitions rather than the actual output of the program. And this exactly is what this optimization is about, where we actually push down the test function to test the individual output, the partial output of individual partition, rather than the final output of the whole job. And this helps us to isolate or localize the exact partitions that are responsible for generating test failure. And by doing so, we can find that failing partition and just localize our search to just that partition. It just reduces the job, the search space of the job quite drastically. The second optimization is prioritizing backward traces. And this is based on the observation that whenever we see multiple faulty outputs, there might be the case where only one input record is responsible for multiple failing outputs. And this is mostly occur when we have operations like flat map or join. So in this case, what we do essentially is we take these two backward traces, we overlap them together so that we don't actually have to solve these two things individually. And by debugging these two failing outputs simultaneously, we just reduce the task and remove any kind of redundant debugging of the same output, same failing input. So the third optimization is based on our observation, where we observed how delta debugging runs, and we find out that delta debugging sometimes tests the same subset of input that is actually responsible for the failing output, and it does it redundantly. So we try to remove that redundant testing of the same input. And what we do essentially is we try to encode the input data, the input subset that we try to test in a bitmap. And here we are not actually trying to read the data to generate this bitmap. We're only using the subset of the offsets of the input data to generate this bitmaps. And this helps us to figure out if the subset of the data is already being tested or not. So now let's look in the demo of BigSift, and let me just set up some things here. All right. So yeah, this is the program. BigSift is just a library that you can import in your Spark runtime. So I've already set up the whole thing. I'm just going to run the program. This is the same program that I've shown you in the motivating example at the start of this presentation. And what you do essentially here is BigSip provides this API where you can provide your application that you're running to this API, and it will just run the program and also sees if there's a problem with the output of the job. So I have already run BigSip. Let me just go to the UI. So BigSip comes with this UI where you can actually interact with this automated debugger. So it first runs the job, shows you the output, and once you see the output in a visual form, you can figure out if the output is correct or not. So now we're just going to wait for the job to finish, and then we'll see the visualization of the output here. So here you can see this is the textual representation of the actual output and the graphical representation. So this is a histogram, and you can see some of the outputs are larger than the other outputs. So you can assume that these are the outliers, and the problem at hand now is to figure out why this has happened. Why are we getting these two values that are extremely large? So what you can do at this point, you can select any of these 5 options. You can either ask BigSip, like, can you please explain what is leading to the minimum input or the maximum input? Or you can write your own test function here, try to tell BigSip like which inputs to debug. So in this case, I'm just going to write this test function here, and we're going to see why are we getting the values which are greater than 6 meters. And I will select this option here and run BigSip. So now the BigSip is triggered. What's happening here is it's going to start running the program, starting with 2 million records. That was the initial size of the data set. And then it's going to run data provenance, and that reduces the scope of the failure-inducing inputs to just 23,000 records. And from that onwards, it starts doing delta debugging to try to figure out what is the precise set of input records that are leading to the test failure. And this is a log scale, so this huge drop here is because of the optimization 1, where we are actually pushing the test function down to the individual partitions. So at different point in time, you can also see this, the view of the fault-inducing inputs. And essentially, you see that these are the 2 records that are responsible for a failing output. So essentially, in my program, I have never encountered this data where we have inches, and the conversion of the units were actually responsible for a faulty output. And it took around 31 seconds to perform this debugging. So I'm going to move back to the slides here. So in terms of performance, we tried to figure out how long does it take to perform debugging, and how much can we improve based on the fault localizability of these tools. So first of all, we tried to run this tool on several benchmark programs, and we figured out that BigSip actually improves the debugging time from 77 times to 66 times over the baseline delta debugging because of the optimizations and data provenance that we use. A more interesting finding that we found that BigSip actually takes 62% less time than the original job time of the job. And this is kind of a really exciting result for us because in debugging, mostly we kind of assume that debugging takes longer than the actual job running time. And to see the progress of debugging here, this is a chart similar to what I've shown on the UI. You have on x-axis the time it takes to do for localization, and on y-axis you have the size of the data. So as in delta debugging, you can see it's a linear decrease on a log scale. So it starts with 1 billion records. It takes around 3.5 hours to find the precise input, which is responsible for a failure. The red line and the blue line shows you the progress of BigSift, where you start out by 1 billion records, and then you find that precise input record responsible for a test failure in just under 13 seconds. Where green line shows data provenance, where you start off with 1 billion records, but then it does not go beyond 23,000 records. So in terms of fault localizability, like I said before, data provenance over-approximates the scope of fault-inducing inputs. So in the green bars, you can see that most of the result that is being returned by data provenance is still in the order of thousands and millions, which is obviously not inspectable by user manually. And the blue bars that you actually cannot see here are actually the results of the result returned by delta debugging and BigSip, which is the precise record responsible for a failing output. So overall, we saw that BigSip can improve fault localizability from 10 to 3 to 10 to 7 times better precision. So in summary, we saw that BigSip is the first piece of work in automated debugging for disk applications. It can provide better precision, 10 to 3 to 10 to 7x over data provenance. We can speed up the debugging time by 66x over baseline delta debugging. And the most exciting result here is that we can actually perform debugging in 62% less time than the original job time of the job. And that's all. We'll be happy to take any questions.
So thank you for the presentation. So just one question. Imagine that we are reading a lot of many different files, and then BigSip will tell you which file is failing. I mean,
it's really hard to hear because the voice is echoing. Can you fix it?
How can I? I can try that.
That's better,
okay.
Yeah.
So is it possible for BigSip to detect the file that is actually creating the error? I mean, the record, you can find the record, but then can you locate the record? Imagine that we are reading many different files.
Oh, yeah, absolutely.
Can you repeat the question for the recording, please?
So the question is that, is it possible to isolate the file which contains the failing record rather than the actual record? So in this case, we can actually do that. So the way that we figure out which subset that we have tested is basically the file that we have used and the actual offset of that data record in that file. So we can definitely find that record and the file.
How can we try it? Is the code published for this?
So the paper is published. The algorithm is there as well. It's just a simple library that you can easily implement. Delta debugging has been out there for a really long time. What you need is essentially a data provenance technique that can actually help you to perform data provenance. You can.
But if you are interested in trying out our software, we will be interested in working with you. If you're asking questions about, do we have a plan to open source our software? I think that's one of the options that we're considering, right? We are currently in the process of getting industry feedback as well as maturing our technology, and we are actively looking for partners to work with us. Yeah.
How about transient data in a multi-step mapping function Spark job? So if we have multiple steps in the Spark job and there is a transient data that's causing a problem, how would that, can that be identified?
Absolutely. I think that's the whole purpose of this work, that you have many steps that your data goes through, and it's really hard to just map the output to the input. And that's essentially what this tool is doing.
Yeah, our work is really targeted for, applications that go through multiple stages of a transformation. But if you're asking questions about how do we go from identifying subset of input leading to a failure to a particular line of a code that's actually wrong or interacting with that data, that's actually what we are working on right now. Like we're working on semantic analysis of a user-defined function. These are arbitrary programs that this data flow or relational operator takes as an input, and we're analyzing actually the code and how it interacts with a particular input.
The code that you've shown is written in Scala. So I was wondering, do you have the same capabilities with Python?
So right now, the API that we support does not have a Python API. We have Java and Scala right now, but actually we're reliant on one of the tools that we have already built called Titan, which actually provides data provenance. And data provenance is right now not supported in Python. So that could be our next task that implement that data provenance tool in Python. The rest of the libraries can easily be implemented in Python.
Okay, thank you.